So after hydroxyl radical has come in and either added to the double or triple bond or has abstracted a hydrogen atom, either case results in this transient intermediate radical located on carbon, nitrogen, or sulfur. And it's at this point that molecular oxygen gets involved in the process. So it will react, the activation energy barrier now to react with that transient radical is much, much lower than it was to react with the initial neutral species. And so diatomic O2 will now come in and participate. Now, like hydroxyl radical, O2 can also react with with this intermediate radical in a couple different ways. So it can react by hydrogen atom abstraction. So let's just show a couple examples of that. So if we take carbon monoxide reaction with hydroxyl radical to generate this intermediate carbon-centered radical, when O2 comes in, it actually plucks off the hydrogen from what used to be the hydroxyl radical. And because it takes hydrogen and it's one electron, that leaves one electron left on oxygen, which then comes and combines with the electron on carbon to form the double bond here, the carbon-oxygen double bond. And so we're left with CO2 and then HOO radical, where there's an unpaired electron on this last oxygen. This is known as the hydroperoxy radical. It doesn't just have to be carbon species, so that sulfur-centered radical that resulted from addition of hydroxyl radical to sulfur dioxide, that will react with the diatomic oxygen. Molecular oxygen comes in and pulls off a hydrogen atom again, and you get recombination of the one electron that's left on that oxygen with the one electron on sulfur to form now a double bond there, and we generate again that hydroperoxy radical. But then O2 can also react in a different way. It can also react via simple addition to the transient radical species. So if we look at that hydrocarbon example where you abstracted a hydrogen using hydroxyl radical to leave you with that carbon-centered radical, then O2 can come in and actually add directly to that radical, form a new bond, and that will leave you then with breaking this double bond to leave you just with one electron on the terminal oxygen. And so kind of a new peroxy type radical. And so you might be wondering at this point, well, how would I know which way O2 is going to react? How would I know whether it's going to add or do hydrogen atom abstraction? And the answer to that question comes down to some bond strength information. So we can look at these reactions and calculate we can calculate the enthalpies for the reaction, following both pathways, whether it adds or whether it undergoes hydrogen atom abstraction, and we can look at kind of which ones might be more favorable. And so if I've got a table here with some bond strengths, I can go through and just do a quick analysis on some of these reactions. So let's just take this top reaction here, reaction of O2 with this intermediate radical generated from carbon monoxide and hydroxyl radical. And let's just look at calculating a rough overall reaction enthalpy. So remember when I'm using bond strength data, it's the sum of the bonds broken minus the sum of the bonds formed. And if reaction is going to be feasible, I ideally want it to be exothermic, or at the very least only moderately endothermic. So I'll look at this and say, well, for this first reaction, I'm definitely breaking an OH bond because I'm taking away this hydrogen here. And I'm also in O2, I'm breaking this bond of the double bond, and so I'm also breaking an O double bond, but I'm not breaking both bonds completely. I'm just breaking one of the two bonds. Like, it's a little complicated, but I'll explain how we kind of estimate to cover for it. And then on the product side, I formed a new OH bond here. And then I also formed the double bond, the second bond of the double bond there between carbon and oxygen. So I've got this CO bond. So before I do any kind of calculations, I can see immediately that I've got an OH bond both in the bonds broken and in the bonds formed. So I can simply cancel those two out since they should have the same contribution roughly. So then I get to analyzing how do I figure out the strength of just one bond of the double bond, both for the OO double bond and for the CO double bond. Well, what I can do is estimate it using the information for breaking those bonds completely. So if I look at the oxygen-oxygen double bond, if I want to get an estimate for just the strength of that second bond in the double bond, I can get that just by subtracting the strength of a single bond from the strength of both bonds together. And that'll give me an estimate for the strength of that second bond in the double bond. So that O, just this bond here, that should just be whatever 494 minus 142 is, and that looks like it comes out to be about 352 kilojoules per mole. So I can write that here, 352 kilojoules per mole. 352. And then I can do a similar analysis on the product side. So I didn't form both bonds in the double bond, I just formed one. So I can get an estimate for the strength in between of that second bond by simply taking the CO double bond strength and subtracting the CO single bond strength. And that should give me a rough estimate for the strength of that second bond. So 799 minus 358 looks like it's about 441 for that. So 441 kilojoules per mole for just that second bond. So then I just do products minus reactants. Well, that's 352. Well, sorry, not products minus reactants. In this case, it's bonds broken minus bonds formed. So bonds broken minus bonds formed, that's 352 minus 441. And I can already see this is going to be an exothermic reaction because it will be negative. But 352 minus 441 is negative 89 kilojoules per mole. So I can say, oh, this top reaction should be favorable because it's exothermic by about 90 kilojoules per mole. So that one seems favorable. Now let's do a similar analysis for this bottom reaction, but let's say instead that I draw it out as if we did hydrogen atom abstraction. So if I draw out that molecule, C, H, 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 C, H, H, radical there, plus O, O, what we're looking at is if the diatomic oxygen came and took this hydrogen atom off, that would leave one electron left, which would come and combine with that electron to form a double bond. So I would end up with CH2, double bond CH2, plus then that hydroperoxy radical that we saw before. So let's just do some analysis of that reaction, say, okay, well, what would happen in this case if we tried to do, is that reaction favorable or not? And then we can compare it. We can do same analysis with the addition reaction that's drawn and see which one's more favorable. So here, what I've got in terms of bonds broken is there's a CH bond broken, and then also I'm breaking the oxygen-oxygen double bond just like I did before. And then on the product side, it looks like I'm forming a carbon-carbon double bond, but I'm only really forming one. I'm really only just forming one of the two bonds. The single bond was already there. I'm just forming that second one. And then I'm also forming an OH bond. So nothing cancels here. I have to go through all my analysis. I already figured out that the second bond of the oxygen-oxygen here, that's only worth 352 kilojoules per mole. And the CH is 441 or 411 from the table. So I've got the bonds broken down. The bonds formed, the OH bond, that's just 459. But then the CC double bond, I'm not forming both bonds, I'm just forming one. So that's going to be the bond strength of the double bond here minus the bond strength of the single bond. So 602 minus 346, that looks like that's only 256 kilojoules per mole, so 256. So then I just take these values, subtract the bonds formed from the bonds broken, and I get 411 plus 352 minus 256 minus 459, and I come out with that this reaction is actually endothermic by 48 kilojoules per mole. Now that's maybe not a ton, but it is endothermic in this case. So what I can do, the last thing I can do is make a comparison with the addition reaction. So this was if I did hydrogen atom abstraction. Instead, now I can make the same comparison with the addition and see what I get there, see which one's favorable. Well, in the addition process, the only bond that I'm breaking is the oxygen-oxygen bond. So in my addition process, I've got I'm breaking that one. So I'm breaking the 352 kilojoules per mole. And I'm forming a new carbon-oxygen single bond. So here, carbon-oxygen, that's 358 kilojoules per mole from right here. And that's really all that's going on. I'm just breaking one and forming one other. So just take 352 minus 358. And this one, it looks like it's actually downhill by about 6 kilojoules per mole. Not a lot at all. But if I compare that to the abstraction reaction, I can see that the addition process is definitely more favorable. I can do the same analysis with this top reaction. I'd done the analysis for the abstraction. I could do the same analysis fairly quickly, actually, for what I would get if I did the addition process there, if I added O2 to that. And I would find that the abstraction process is more favorable. It really has to do with the fact that we're forming, the differences between these two has to do with the fact that we're forming a carbon-oxygen double bond versus here, if I did abstraction, I was forming a carbon-carbon double bond. And if you look down on the table, just a quick comparison, the carbon-oxygen double bond is stronger than the carbon-carbon double bond. So it's more favorable in the top case where I would form a carbon-oxygen double bond to do abstraction. Whereas when I'm only forming a carbon-carbon double bond, it might be more favorable to do addition, as it is in this case. So I hope that's helpful in sort of getting a little bit more of a handle of which pathway the reaction with O2 will take. In the next video, we'll look through, we'll look at some subsequent reactions and how we actually regenerate hydroxyl radical from the product of the subsequent reactions with O2.